So here we are with the continuation of our discussion on the business mathematics and statistics. So for those who can remember our initial plan on the subject areas that we are about to cover, I'm very pleased to announce you that we have covered almost 50% of the uh, areas that we were supposed to cover with our previous discussion on the confidence level estimation and with the continuation of the probability theory. So that was our fifth and sixth lessons, and sorry, that was our fifth lesson, and today we are stepping into the next 50% of our syllabus, that is on the lesson number 6 onwards. These are the interesting areas, students, where you need to really focus on, because if you really look at the subject areas that we covered so far, areas such as charting, sampling, the very first area on the nature of data, primary, secondary sources of data. I mean, those are stepping stones actually. But the lessons that you see from the 50th percentile onwards, the lessons that you're going to start from today onwards, are the good lessons that you can apply in your job at the decision making level at one point, and B, these are the essential areas that will be questioned heavily at the examination. If you look at the lesson that we are going to learn, that is under the regression analysis, uh, you may see at least one complete 20-mark question in the past couple of exam papers. Personally, I haven't seen this year's paper so far, but we'll take a look at that also. We'll have a detailed discussion before the examination, at least the last paper. I believe that the trend would have been continued, and there will be some 20-mark good questions from areas like uh, modeling, regression analysis, NPV, portfolio theory, so on and so forth. So uh, from this point onwards, probably we'll be spending one class on theory and one class on entire one class on the recent examination questions. I think it is paramount for us to spend the second class's time more than the first class because of the theory. You will learn a lot of surrounding aspects into one subject area. But if you really look and focus on the second class, which we are going to discuss the examination questions, that is the real essence that you will find as to what depth the examiner is expecting you to have the knowledge and what sort of assumptions that you have to make at the examination, the nature of style of writing, all these things are very important. So that's why uh, from linear regression to indexes to modeling to NPV project appraisal, we'll spend not more than one class on theory, and the second class will be entirely on the examination questions. Okay. So having said that, we are lacking, I mean, we have really tried to compress all the theoretical areas into one lecture. So I believe that, I wish that if I had some time to, recap with you, maybe half an hour, and discuss the first 50% just to recap. But I believe that the videos recorded are also available. So if at all you have any doubts on our previous discussions, I invite you to go through our recorded videos, and I have shared my email with you. If you have any doubts, you can drop an email. So we'll have a bilateral conversation and try to clear out your doubtful areas. Okay. So with that background on mind, we are going to start our lesson number 6 today. That is on the linear regression analysis and forecasting. So these are the subject areas that we are going to discuss today. We have time to go through all, and this discussion of the past papers, this particular one, we will be leaving out to the next class. Okay. So first of all, we will get an introduction to the regression analysis. I mean, as usual, all my other lessons, I really want you to give an introduction as to why we are learning this subject area first before we move on to the theoretical area on what is regression analysis. So once these two areas are completed, we will be learning these two branches of regression analysis. One, the very first one is on the simple linear regression, and over here in area number subject area number 6, you can identify the multiple linear regression. So these are the essential two branches of our today's learning. What is this simple linear regression and the secondly multiple linear regression? Uh, so uh, when you learn regression, you will understand that this lesson is all about finding some sort of uh, statistical relationships between maybe two variables or maybe multiple variables. So in area number 4, we will discuss plenty of statistical relationships that we can find in the real world, like when a certain variable is going up, what happens to the other variable, whether we can find both are moving to the same direction, opposite direction, why is that? So there are some practical scenarios which we can learn and discuss and understand deeply. This method in subject area 5 that we are going to discuss is the only method that we have to learn under today's lecture. We call it the ordinary least squares method or OLS method. OLS method. So this is an this is just only one method where we can use to calculate the relationship of a two variable instance x and y. We are going to use this particular method and understand how to find this relationship in a statistical way. The output is nothing much, nothing serious. It is going to be somewhat sort of like an equation. So we will be using this method. So in the latter part, when we have been introduced to the multiple linear regression also, you will understand the same method could be used, but then again, we are discussing more than two planes, xy plane and xz plane and zy plane. So it's going to be a bit more complex to discuss the application of finding a best fitting line, but rather we will just see some practical aspects of what sort of multiple linear regressions are there and how it is being used in the real world. Even if you look at the exam questions per se, the examiner is not keen to ask you for calculating some sort of a relationship by hand for a multiple linear regression, but he or she will be very keen to give some sort of a relationship to you and ask for your interpretation. So that's the essence of this course. This is not a statistics course, rather we are studying banking here. So area number 5, area number 6, the expectation is for you to understand what the concept of multiple linear regression is going to tell you and to form an equation and to express their variables, what they say, how you take decision. Lastly, we will discuss about this coefficient of determination. We call this value as R square also. Sorry, R square. Sorry. So this value is going to give you some hint as to whatever the relationship that we are going to find for these two variables and multiple variables, whether it's going to be a successful one or whether what sort of a coverage. Or are we looking at whether have we covered 50%, have we covered 90% kind of a relationship of the defined equation. The last part, area number 8, will be the next lecture. We'll spend an ample day on all the recent examination questions, different types of questions. We may be not in a position to cover maybe 10 or 20 questions, but rather we will spend time on at least each type of questions in a recent examination paper. If there are multiple types, I'll make sure that we cover all different types. So you're in a very comfortable position closer to the examination. So that's the plan for the day, and we'll move on with the today's lesson and try to learn something totally new, the regression. Okay. So students, if you can recall our some of the initial discussions into graphs and charts, I think that lesson must have been in lesson number 3 or lesson number 2. We discussed that there's something called a scatter diagram, and here we are not spending time to discuss it, but rather it will be used in a couple of lessons from that point onwards. So during one of the last lectures, we learned to form up a normal distribution or a standard normal distribution. We are going to use nothing but a scatter diagram. So what does a scatter diagram tells you? In simple form, if I just draw one for your purview, it is going to tell you a smaller relationship of two variables. So let's say you have two axes like this. We call this as the x-axis and this as the y-axis. Okay. So like in any other instance, so once you plot the individual data points like this, we call this as a scatter diagram. Why it is scattered is because of the fact that data points are at different individual levels. For instance, if this is one particular data point I'm going to discuss with you all, this is the data point. This has a particular x value. Let's say 6 is the x value and y value is 3, and this data point will be expressed as 6 comma 3. Now this lesson that we are going to learn today, the regression, is based on this scatter diagram concept. In reality, if you plot a normal line, something like this, with a nice two variables, we don't have to go for a regression. Why? We have figured out that this is nothing but a y equals mx plus c kind of a line. Or one could say this a plus bx. Another form, alpha plus beta x. Different forms, but then again, if you really look at the nature, it has only variables, y's and y's and x's. So all the other m, c, a, b, alpha, beta are going to be some sort of constants which are unique to the line that we have drawn here. So if this is done and if you know this, then there is no need to learn this lesson and do a regression analysis and try to figure out a line. But why do we really need this lesson? In reality, the data that you see, which will have a two variable example for our initial discussion, there are multiple variable instances also, but for the moment, let's think that we are discussing a x, y kind of a normal variable relationship. So in that instance, if you know this, line, then there is absolutely no necessity to come up with a regression. But the real world data are something like this. Let's say this is the height of a student, my famous example, and uh, this is the weight. If I just put up some random students and draw some sort of a scatter diagram like this, I will never find a perfect best fitting line like this. Rather, I will always find a scattered set of data which is being nicely plotted in a 2D dimension like this. It's all scattered. These data points have no any relationship as we eyeball it. As we glance through it, we can't really identify any relationship. Someone would say, okay, now if I plot a data point like this, okay, now this seems to be an outlier data point. One could argue and say, okay, this also seems to be an outlier. So in nature, students, this is what you can see, and this is all what you will get when you take real data and try to do some sort of a study or an analysis or a research. Okay. So the idea of regression is going to be to find statistical relationships in different domains like finance, investing, maybe medicine heavily, trying to find relationships between two or more variables. I repeat, trying to find relationships between two or more variables. So the jargon that we're learning, the mathematics and statistics, is always going to give an output, a defined output, always. It's not a qualitative paper like economics, sociology, or psychology per se, but rather you have to find an answer. You have to give a number, or for a given number, you have to give an explanation, an analysis. So similarly, this regression will give you an output in the form of an equation. So typically, students, the regression is all about if I simplify it to the absolute basic levels for you to understand, for a scattered set of data, we are going to define variables. And for those variables, we are going to find a equation of best fit. Why do we need to do that? It's going to be a hazardous process. It's complex. It has a lot of equations to apply and a lot of steps to follow. But why do we need to really do that? It is merely because of the fact that we need to make decisions. We need to make decisions. So, under probability theory, we learned that any decision in our day-to-day work professional environment is going to be a decision under uncertainty. There's a reality who absolutely never you will find an opportunity to make a decision with certainty. Always there is a decision with uncertainty. The classic example, the domain that I'm coming from, investing. If I just recall an example. Let's say I want to invest in a particular asset class. Let's say, for everybody's understanding, a share. I want to invest in a share. Uh, so what is going to be my basic question is the fact that do I like to buy at lower price and exit at a higher price? Of course, that is going to be my target. But what's the reciprocal? What's the downside? If I buy at a price and if the price of the share goes down without any hedging, without any derivatives, if the price of the share goes down, then I will be not very happy. I will be feeling that I have lost my capital. I will feel a little bit of a pain. Now, what have I done? I have made a decision under uncertainty, and the variables that I use to make my forecast is not seems to be correct. Or maybe there are more variables which are going to move the share price to the adverse direction, which I couldn't predict at my prediction or my analysis level. That's the usage of this regression. So for you to understand, well, irrespective of the domain that we are working on, I assume that a lot of us will be working in the banking domain. That's why we are pursuing this course. So there will be a lot of instances that we are going to make calls with some uncertain set of data or with a data set without any perfect correlation. So students, that's why we are learning regression, for us to find some relationships in such circumstances. If I take you through the wordings, regression is a statistical method used in finance, investing, and other disciplines that attempts to determine the strength and character, the strength and the character of the relationship between variables. It could be true, it could be more. So the two types that we'll be learning under this curriculum are simple regression and multiple regression. Students, simple regression is nothing but we are going to discuss some relationship between two variables. Two variables. Multiple regression, more than two variables. Look at these examples for simple regression and multiple regression. Simple regression. A relationship between age of vehicle and the cost of maintenance. Age of vehicles and the cost of maintenance. Typically, when you look at this wording, what can you assume? You can think, okay, if if the age of the vehicle is somewhat higher, we will have to bear higher cost of maintenance. Isn't that so? Can you find a vehicle which was built in 1980s and 1983, 1985, and run without any maintenance? It's not going to be the case. The vehicle is very old, so typically there's a tendency that the cost of maintenance is going to be very high. But what if you buy a brand new car from Toyota or Nissan or Honda, or even a European one, with a zero mileage, and the year of manufacture is 2020 or 2021. What would be the cost of maintenance? The first couple of years, absolutely, you will be only having some recurrent expenditure like fuel and all the lubricants and some of the replaceables. That's all. But the major maintenance like the sensors and all those things will be not really there. So what sort of a relationship that are we going to find here? If I just try to determine some relationship, higher the age of the vehicle, higher the cost of maintenance it is going to be. So I'm going to move this particular variable. Cost of maintenance, okay, one could say, okay, it's both side. You can find relationships. Yes, that's correct. If the cost of maintenance is high, typically the age of the vehicle should be higher. But don't forget the fact that there are many other factors. If you are talking about a European car with a higher spec, typically the cost of maintenance is going to be higher even in the first couple of years also if you get a maintenance. But on the other hand, if you try to move the variable other way around and find the relationship between the uh, vehicles with a higher age and the cost of maintenance, okay, you are going to vary the age while you will observe the cost of maintenance at y. Easily we can find these kind of relationships of two variables, and if you get plenty of data, we can do a regression and find the best fitting line. Look at the second example for multiple regression. I'm quoting the same example, but here I'm going to bring in some more variables. Sorry, relationship between relationship between the cost of maintenance of vehicle, age of the vehicle, brand of the vehicle, and purpose of usage. Okay, I have got some many more variables here between the cost of maintenance and age, brand, and purpose. See, in the previous instance, if we try to take cost of maintenance as the x variable, obviously now you can understand that there will be many more other variables which is going to change the cost of maintenance. If it is an expensive brand, and let's say if it is being used on a daily basis, if it is being used in a hill country, or maybe for transportation purposes of passenger transport, versus a vehicle which is lying in your garage, you can find the cost of maintenance is going to be significantly varying from one vehicle to the other. What are these examples? These are the instances where you can find either a relationship between a given two variable, or for a given variable, multiple other variables is going to change the value of that variable. Now there we are going to get ourselves introduced to this wording of dependent variable and independent variable and label them, and then only we can find these relationships. So hope you get a bit of an idea of what is regression and what we are going to do. It's nothing but finding statistical relationships. Okay. So here we are going to define the dependent and independent variables. I'll take you through the notes. Regression analysis attempts to explain the movement of a dependent variable, or statistics we call this as a response variable, based on one or many independent variables. Exponential variables also being used as a word. In simple form, dependent variable, the typical form that we are labeling it is going to be as y variable. Independent variables, typically we are giving the word of x variables in mathematics and statistics. The regression analysis, I am not going to limit myself into simple, but multiple also I'm going to define here. See, based on one or more, one or many independent variables. So there may be either a case of 1x, or could be x1, x2, x3, kind of a multiple instances also. Don't be scared. This is very simple. You will understand what these multiple variables are when we do one or two examples and the relationship. Moving on, second point. We can also utilize regression to forecast or predict the value of response variable, that is y, from the values of one or more explanatory variables. Now students, this is the essence of our lesson. This is what we are going to do essentially once we are done with the regression analysis, and this is the usage of our regression study. Let's say, draw a small scatter diagram again here for our discussion purpose. I get a set of data like this, scattered all over the place. And let's say, some or the other how I found a line like this is going to represent this data set. What is this? This is the x variable. What is this? This is the y variable. The dependent variable, and x is the independent variable. What is the second bullet point is going to tell you? It is going to tell you that we can forecast or predict the value of the response variable, that is this y variable, from the values of one or more explanatory variables. Now students, we know from our earlier studies, if we know a line, and for a unknown x variable x, y, we can use this particular line and forecast the value for y variable. This is going to be y5, y5, using this particular line. I'm sorry, this particular point has to be, sorry, wait, in the correct way. This has to go and touch here. Okay, so that's the whole idea of the regression analysis and the forecasting and predicting. Once we are given a particular line, then the life is very easy. But the whole idea of our lesson is to understand how to draw that line, different methods that we can use to draw that line, as well as once we have the line, how to forecast or predict for a given unknown value. But then again, one could think, okay, uh, if we have a best fitting line, can that line represent everything? I mean, why do we have the word of best fitting? Can't it be a perfect fit? Why are we always talking about a best fitting line and a prediction and a forecast? Can't there be a perfect relationship which is going to tell any movement of our dependent variable with the values of independent variables? Students, we have to understand that in the real world, in the statistical jargon, the linear relationship is not the only type of relationship which is available in there. There are different natures of other relationships which you can see in the real world. Categorically, if I got maybe one or two curvy linear relationships, it's not a perfect. Let me just try to put an example for you. It's not going to be a perfect line, but rather it is going to be a curvature, sort of like a curve. Can you see my screen? Let me reshare this. Give me a moment. Okay, while the screen is coming up, let me explain. Let me continue my explanation. So maybe the relationship between these x's and y's can be explained with some sort of a curvy nature line, a curvy linear line. Sometimes there are exponential lines. In mathematics, we call y equals ex, e to the power x, an instance of where x variable is no longer in the y equals mx plus c nature, but rather x variable is now in a power. Y is equal to e to the power x, e to the power x square, e to the power x plus y, sorry, not y, x plus z or any other value. So in reality, you can find different kinds of relationships. But in regression, we have to understand that if you're talking about a simple linear regression, we are always trying to find a line, a straight line between variables, between two variables. But in reality, you can understand that there are going to be many different types of relationships which will effectively diminish our study, which will not really give us a, fruitful outcome for us to discuss some relationship between the two data. You will realize, you must be wondering at the moment, okay, if that is the case, if there are no any perfect relationship between two variables, then how can we rely, or how can we depend on a particular data set when we forecast something, or when we use statistical some sort of equation? Can't there be errors? Of course there are going to be errors. Hmm. There are going to be errors which is beyond our control. Some of these errors we cannot really use. Some of these errors you can minimize. In instances, sorry, let me restart my screen. In instances where when you don't have the best fitting line, or maybe when you have a r square, or a value which is going to give you, let's say, some sort of a 30% coverage, or the equation that you're going to find is going to cover only 25%. So in such instance, you can understand that, okay, uh, we are not going to use the line that we found in a way, because that we are sure, we are very sure that that particular line is not the best fitting line. But in that case, can't we do some sort of a different methodology and find the best fitting line? Of course there are, but we cannot discuss those kind of different methodologies under this curriculum. Why? Because that we are going to only utilize our knowledge on learning the simple and multiple linear regression and the practical aspects of it. Okay. Let me quickly restart my whiteboard and share the screen again. If you could recall, in our early mathematics days, if you can remember that y equals x square plus 2x plus 6 kind of a relationship. Sometimes you may have remember that we can draw that graph also. There is a maximum point, there is a minimum point. Those are also relationships. Those are not linear but curvy linear. So in instances where you can find such relationships, we have to always be careful. Uh, why? The linear relationship that we are going to find under this regression is not going to be a perfect fit. Okay. Can you see my screen again? Okay, fine. I got it back. Okay. Now, students, moving on to the simple linear regression. This is the form of equation that we are going to find in the end of the day. You can recall this with the simplest form of equation that we are using so far. That is nothing but, sorry, there is going to be nothing but simple y equals mx plus c. Hold on. Yeah, something like this. Y equals mx plus c. What is this form? There is a simple y variable, and there is one x variable, and then there's two values which is going to determine the shape of a line. So this is going to be the x, this is going to be the y, and of course we call this gradient. We call this as a tan theta of this particular line's angle as the m, and this small value is in the corner. We are going to call that as c. Y equals mx plus c. The exact similar form is the one that you can find here. What is that? Sorry. That is going to be y equals alpha plus beta x plus another sign which you don't understand at the moment. Y equals alpha plus beta x plus, we call that value as the epsilon. This value, which is similar to an e, we are going to call that as epsilon. I'll take you through the notes. Simple linear regression is a method that studies the relationship between one independent variable and a dependent variable. So we've been discussing this again and again. Now let's see. Since we consider only a single independent variable, the word simple is used. It's because of the fact that we have only one variable to the explanatory variables movement. This response variables movement. This y variable is the response variable, and this x variable is the explanatory variable. In other words, x is independent, y is dependent. And these alpha and beta are parameters that must be estimated. We don't know these values and we have to estimate it. This epsilon, this problem child, this epsilon is the error term. This implies the absence of an exact relationship. Now, this is the answer for the last discussion. This is going to imply the absence of an exact relationship between x and y. So, if you can recall our scatters, let me try to scroll to one of here. Yeah. If I draw a line over this scatter, something like this, and then what if I'm going to explain this particular data point I'm going to highlight here, this particular point I just highlighted. How can I explain? I mean, it's not in the line, isn't that so? There's some sort of a gap between this particular line and this particular point and the line that we explained. Now, students, that is the error. That is an error term for these individual data points which is coming after a study under this particular method. Can we minimize that error? Of course we can, and absolutely that is the answer that we are going to try to find through that ordinary least square method. At the end of the day, when we do the ordinary least square method, if we can find the error or the epsilon as 0, that's an instance where instead of a scatter diagram, all these scatter points have now merged to one nice best fitting line. Not that their values have changed, but rather we have figured out that, okay, there's no scatteredness, rather all the points are nicely coming into a straight line. That's about it. This is the form that we are going to use. This equation is not to be applied, but rather for you to keep in mind. I mean, it's not really wrong to use this y equals mx plus c kind of a wording, but you can understand from lesson to lesson, from subject to subject, there are some norms and practices. So alpha and beta are the terms that we are going to use for regression equations. But don't be scared. This is nothing but similar to y equals mx plus c plus some kind of a epsilon kind of a equation. Okay. We'll move on and try to find some more data on this epsilon, this error term, and how to minimize it. But before we go there, I want to take you through some of the statistical relationships that we can find in the real world. So we can observe positive or negative relationship between two variables when we plot them in a XY graph or a scatter graph. What are they? They are positive or negative relationships. Okay. The first one I'm going to quote is the positive relationship between the height and the weight. My classic example I'm quoting always. Height and the weight. Sometimes if you go to a doctor and try to measure your weight, there you may have seen some sort of a graph called BMI, body mass index. What is this graph is going to tell you is that for a particular, I mean, for all the typical human beings in the world, they have plotted this graph with the height and the weight. So given the height of a person, there is a recommended weight. If you look at that particular table, what sort of a nature that you can find? Higher the height, the weight value also higher. Higher the height, sorry. This is going to go high and the weight is also going to go high. In such instances, students, we call it as a positive relationship. We have learned already this under our initial studies on standard normal distribution. This is the same thing. Reiterating and quoting up with some real world example. Look at the second one. Negative relationship between the interest rate and the share prices. Now these are good times to discuss this example. Last year I recall that when this is being discussed, uh, I mean, for myself also, I have only seen this in one instance. In 2008, post-war, we could see the share prices are blossoming up. Now, in the current scenario, you can see the interest rates are pretty much lower and the share prices are coming up. Now, the Sri Lankan case may be one particular unique instance that we can explain under different variables and different circumstances. But in developed markets, if you really look into the economic cycles, students, you can understand when the interest rates are higher, the share prices are typically tend to be lower. And when the share prices are lower, interest rates tend to be typically higher. Why is that? The investors move money from one instance to the other instance, one place to the other place, one investment to the other investment. If the interest rates are maybe 12% or 13% from our context, we can say it's a fairly high interest. And in such instance, people would really love to, not to take a risk and go to share market and make investments and make losses. Rather, they will be very much happy to put their money in a bank or a debenture or a treasury bond or a bill and get a secure return. But rather in times like when interest rates are pretty lower, people really don't find interesting to go to a bank and get a low number like 3% or 4%, and they will typically try to go and find more excess risk and get better returns. So that's why they typically come to share markets, and when the demand is pretty high and when abnormal number of chaps are coming to the market, share prices will have a abnormal demand, and that's the reason for the prices to go up. So these are some cyclical relationships that you can see in a lot of developed markets. Third one, positive relationship between the foreign direct investments, FDIs, and economic growth. If there are more foreign direct investments coming, that means directly foreigners are pumping up their money using the hard currencies, like it could be dollar, it could be euro, pound, kind of stronger currencies. When they are moving in with the direct investments, economic growth is going to be very much higher in such developing economies. Last one, negative relationship between the GDP growth and unemployment. Similar typical example. If the GDP growth is higher, we can find, okay, that means a lot of people are contributing to the GDP, to the economy to grow it fast. But if it is lower, we can find the vice versa. That means a lot of people are going to be jobless, homeless, and they will be depending on welfare economics. Now, these are some of the statistical relationships that we can find for a nice two variable kind of a example. Okay, look at the graph that I've given here. I have the real GDP growth and the change in unemployment level. So these are some of the scatter points that we can see. So they may have, plotted this for, yeah, it's there from 1961 to 2013. Plenty of data points, maybe 30 to 40. And when they plot it, now this side, you can find real GDP growth is going to be higher. This side, you can find the unemployment rate is going high in negative territory. That means it is reducing. And once you do this best fitting line, what can you find? You can find a nice negative relationship like the one that we have found here. What is this? I've got in the example which is in the graph. Pi is equal to negative 0.37. There are more decimals. I'm going to stop here. Plus 1.23. This is the relationship for the best fitting line that they have figured out with this regression study. Forget about this R square for the moment. Just focus on this equation. That's the output. Okay. Now we know some few relationships for two variables, and I hope some of you must be eagerly willing to know. Okay, enough about the chapter, and let's learn how to do this business and calculate this. I mean, why can't we merely go and do this by hand? Is there a method? Of course, there's a method. In maybe grade 10 or grade 11, you may have recalled that when you are being given this nice, there's this different type of A4 sheet which is having some sort of a nice grid when we used to use for the mathematics those days with the minute 1/10 of a fraction. We have done this exercise previously. We all have. Uh, it's the same method. We plot the scatter points, and then the teacher is coming and giving us a ruler and asking us to, draw a line the way that you think. The way that you think. There is no scientific method. Just draw a line. The way that you think is going to be the best fitting line. Once you draw that line, since we have drawn this in the nice specific A4 sheet with all these grid that we are using, then we can calculate the M and the C for the y equals mx plus c method. So it's the same thing, students. If you have maybe 10, 12 different data points, you can forget about all these theories, do the same exercise, and still find the best fitting line. We call it an eyeballing method or best estimation method, or just on the face value of it. You can call it the way you like, but the essence is that without any theory also you can find a best fitting line just by looking at the data points and estimating that it is going to cover the maximum amount of points. Okay. But here, from this point onwards, what we are going to do is that we are going to scientifically learn the one of the most widely used methods in regression, that is the ordinary least squares method. And using that method, uh, without eyeballing, without drawing any graphs or lines, for a given set of data points, how to calculate the best fitting line. That's the idea of the ordinary least squares method and the usage particularly. Okay. Fine. The ordinary least squares method, a linear least square method for estimating the unknown parameters in a linear regression model. So far, we have given ourselves the introduction into y equals alpha plus beta x. But if you carefully look at this equation, you can find that instead of y, I have put this y hat, actually y hat. You will understand why I have changed from y to y hat in a little while. And epsilon, this error term that we talked about previously, is going to be the differences of the y minus the y hat values. So what is this y hat? Y hat is going to be the predicted value, the calculated value. And yi, I'm talking about these individual data points. Huh? These are nothing but I'm talking about all these individual data points. There are xi, yi, sorry, x1, y1, x3, y3. Now these are the points that I'm talking about for this y hat and this yi. Huh? This, yeah, now this y hat is going to be the predicted value, while yi, the values that I've just drawn, this y1, y3 are the true values. And this epsilon 1 or the residual is the error which occurs when individual points of y values is fit into the regression line. Now those are the definitions. Don't get worried. Let's just try to use this graph and understand what these hats and epsilons are going to tell us. Okay. Now, what are these blue colored dots? These are those scatter data points that we discussed a moment ago. Categorically, this point, this point, this. Now, these highlighted points are the 6 different points in this data set. We only have 6 different points. That's fine. And the line that you can shown here, let's assume that I have drawn it by using this ordinary least squares method. Let's assume that this is the output for the moment. Now, if I take one particular point, let's say for this particular given point of x1 and y1, these are the actual values. Okay. Look at this point 2. This may be also coming as x2, y2. Similarly, for all these different points, we have x's and y points. Now, what has happened here is that instead of this y2, this y2 point will have to be moved to y2 hat. Let me repeat it since this is important. This y2 value I'm highlighting have to go and move to this y2 hat value. There is a movement like this. Y2 is going to move from here to here and just reverse small arrow also. Similarly, students, if you look at all these other values, this y1 have to come to y1 hat value. If this is y3, this has to come to y3 hat value. If this is y4, y4 hat value. Similarly, if this is y5, it has to come to y5 hat value. What is this hat value? It is nothing but if this particular equation, sorry, if this particular line with a particular equation is going to explain this relationship, these movements has to be made. There is no choice. These points has to come to the best fitting line. Why not x points? Because of the fact that x is the independent variable and we really cannot change that. We are observing the dependent variable y's movement because of the x variable. So we really don't want to move the x points and tally to this particular chart. Rather, assuming that the best fitting line is done, assuming that this is done, this line is okay, we are going to slowly move these individual data points y variables to the value that is being drafted in the given line. Now, each and every of these y minus y hat values are the values that are going to be utilized from the next point onwards. Students, what are we going to do from here onwards is that we are going to minimize the individual, these arrow points that I have drawn here, individual y minus y hat values are going to be minimized. If you just try to visualize these red points, now change the color to red. What if these red points are encultivated to the points of these lines? Then what will happen? Obviously, we can find a perfect line of y equals alpha plus beta x. Isn't that so? If that is the case, we are very happy. No need of regression, and we are happy that okay, now all our data points are going to be explained with this nice line. But in reality, it is not the case. It is not the case. So the ordinary least squares method, students, it is trying to find the minimization, of this particular best fitting line. But now I told you at the beginning of the argument, let's assume that somebody has found this line. That's what I said. Let's assume that, okay, I found this line. But can't there be many more lines? There can be. If I just use a different color and try to show you a different line, okay, I can draw for the similar this thing, a line like this. What about that line? Or if I use a different blue color one, a line like this. Now these all are going to be best fitting lines, isn't that so? But what eventually I'll be doing is that for all these different lines, for all these different, the black one is there, the other blue one and the green one, for all these different lines, students, I can do this exercise and find the value for this particular yi minus y hat I to the squares sigma. For this particular value, I can find the number y as in why. Why is because of the fact that once I do this exercise and calculate this particular instances, I will be end up with a number, isn't that so? What are those numbers? If I just let me just take a different plane and take some values and give you a glimpse. Let's say this is that line that we discussed so far, and I'm going to just take one value. The real value for this is going to be, let's say, 3 and 2. This is 3, this is 2. And this particular point, the height is higher. It is going to be 4. Okay. Now, what is going to happen? Instead of 2, instead of 3, 2, now I will have to uh, go and find the value 4 as the best fitting line. What is the gap? The gap is, oh, sorry, I think my screen is no longer being shared. Okay, anyway, let me continue the discussion. The gap is 2 minus, sorry, 4 minus 2, the value is going to be 2. Okay, that is one example. But what if I draw a different line, whole different line? Okay, let's visualize this for a moment. There's a different line with the y value is going to be 5. Now it is not 4 anymore. That particular line, if I just try to move this x value, it's not going to be 4, but it is going to be 5. So what is the gap? Previously the gap was 4 minus 2, it is just 2. But here the gap is going to be 5 minus 2, that is going to be 3. The gap is somewhat higher now. Okay, it is higher. Now are we happy? No, not particularly happy. Why? Because of the fact that the second one, uh, the the second graph that we just visualized has a higher deviation compared to the one that we discussed. So obviously, where we'll be happy is going to be with the second one. But what if I find a you know a line with even narrow gap? Maybe okay, my screen is back. What if I find a line like this? This gap is going to be even reduced. Now this gap is 1. The previous gap is going to be 2. And this other line, this gap is going to be 3. 3 is higher, 2 is lower, and 1 is the best one. So we were only discussing about one particular point. But eventually, students, what we were doing under this ordinary least squares method is that for all different points, we have to calculate this y minus this y hat value. We take the square and take the summation. Why do we take the square? Is to answer the question of avoiding the negative values. Either we can take the modulus value or take the square value, whichever is fine. But under this method, we are taking the squares. Once we do that, the whole idea is that we have to minimize this particular value. So let's say you have done maybe 3 or 4 different lines, and out of all these 3 or 4, you just found one particular line with the minimum value. I go back to my previous plane. Okay, let's say for the blue line, my epsilon, this sigma value is going to come as 2.3. For the green line, my epsilon value is going to be, let's say, 1.6. Which one I am going to be happy with is obviously going to be the green one. Forget about the fact that this is only just 1 point. Let's assume that there are all the different points and we have taken the sigma for the error term, and here we have find a better point than the previous 2.3. So that is the ordinary least squares methods output. That is what eventually we are going to do. Don't worry, we will just have one class example and calculate with hand and see. Forgetting about the fact that we are going to draw lines and find this number. In reality, once we use the method, there is one or two equations to find the a and b, or alpha and beta of this particular equation. I mean, as long as we can find these two values of alpha and beta, we are done. Why? Because of the fact that x is a variable, y is a variable, and if we can find the values, then we know the line. That's the whole idea of our next couple of minutes. This particular term, now I told you the error, we are going to sum it up and look into the value. Just observe the value that 2.3, 1.7, 0.7. Now these are the values that we just got for this epsilon. In statistics, we call this as the sum of squared error, or SSE. Sum of squared error. That is sigma I equals 1 to nth epsilon I. Or individual errors, we add it up. So we have the summation. Or when you look into the final definition form, this is the equations form. This is nothing but we have taken the differences, that 2 minus 4, 5 minus, sorry, 2 minus 4 minus 2, 5 minus 2, those differences we have taken the squares, nothing but. So regression line, the second bullet point, regression line is a line which is drawn across the scattered diagram, which is minimizing the SSE, sum of the squared errors. And once you found that particular line, we are done. We call that as the best fitting line. And once we are done with the line, eventually we can play around. We can forecast the next particular values of any unknown. Okay. Fine. Now this is the equation that we are going to use for this ordinary least squares method. We have learned this previously. The correlation, we are going to utilize that. Okay. Now this regression line, I mean, if we are the mere formation of it, we call it, I mean, we used to call it as y equals alpha plus beta x plus this error term. And we know there's a particular method that we are going to use to calculate the alpha and beta, and subsequently we can discuss about this error. Okay. And this we are converting to this y hat and alpha hat and beta hat form because of the fact that now we are going to use the individual scatter points and equate it to a point which is going to be calculated by using this equation. Repeat, we're going to take those individual points of x's and y's, and we are going to compare that with a particular set of values that we are going to calculate with this particular set of equations. Okay, so this beta and alpha, which is shown in this equation, can be calculated by using these equations. Beta, I mean, for the moment, let's assume, I mean, we'll start with the calculation of beta, and then only we will move to alpha. If you merely, I mean, try to recap our earlier discussions, we merely have, let's say, two different points. Sorry, I have to draw this a little bit bigger. Students, just forget about the fact that we have alphas and betas. Let's just discuss the very basic form that we know so far, that is on the y equals mx plus c nature. This is going to be y equals mx plus c. How do we calculate this m in our childhood? Is nothing but we are only taking two values and we are assuming, okay, this is a perfectly straight line. This is going to be, sorry, this is going to be x2, y2, and this is going to be x1, y1. Sorry, this is x1, y1, and this is going to be x2, y2. Simplest form is that we assume that there's a small triangle like this. Then we take this particular height, the difference between these two ratios. That's how we calculate this particular m. Or sometimes we used to call this as tan theta of this particular value is also going to give you the value for m. Here also, students, under this regression, now we don't have a perfectly fitting line like this. If you try to complicate the scenario, it's no longer like these red dots. Rather, it is like these blue dots. So this is here and this is here. Now we are complicated and still this is going to be the best fitting line, but we can't really apply this simple form. So that is why, students, we have to find this beta and alpha with this covariance and variance relationships. If you just focus on the equation per se, the equation, the one that we have done previously. This is nothing but the covariance between x and y divided by the variance between x variables. If I take you through the equation, sigma xi minus x bar yi minus y bar divided by sigma xi minus x bar square. Or I can quote another example. Xy. Now, individual data points, I'm multiplying the x to y and then minus the x bar y bars multiplication divided by x bar square and sorry, x squares bar and x bar squares. Now, for instance, what is this x bar and x? This x bar is going to be the average of individual x variables. You have data points like this. This is x1, y1, this is x3 and y3. If this is the nature, these x3s, x1s are going to come and help to calculate this x bar. That is the same x bar. This is nothing but the arithmetic mean or the average. So in statistics, similar to this form, there are many other forms that you can calculate this covariance and variance and find the beta, but bear in mind that this is the easiest form for you to remember. Divide the covariance between x, y to the variance of x. Okay. And let's assume, don't worry, we have a small class example for you to get yourself very clear as to what these individual values are and how we are going to calculate. Once we go there, you will be clear. So assume, students, now we know the beta for the moment. We know the beta, we are only left with calculating alpha. And I told you at the beginning, okay, when you have these x's and y's, x1s and x3s and y1s, y2s, different values, we can calculate the known values like x bar. So for a known point, if I use the points of x bars and y bars and apply beta here, with that we can calculate the alpha. I repeat, for a known points of x bar and y bar, if we use the value of beta to the same equation, absolutely we can calculate the alpha. Or you can use any other different points in the equation also. So there's no hard and fast rule here. That's the components of beta and alpha computation. So I urge, don't worry, forget about this complex equation. Just keep this form in your mind on the covariance and variance calculation. This is enough. And once you know the ingredients and where to apply and how to apply, you can easily calculate beta. You know the x bar, you know the y bar, you can use these couple of values to calculate alpha. Then we are done with the equation. Okay. So before moving on, to a computation in the next slide. Let's see some of the assumption in this method. Since this is a statistical method, obviously there has to be limitations and there has to be assumption. Okay. Now these are some of the points. If you look at some of our 20-mark questions and some of our 2-mark questions in the part number 1, these are some of the things that are very hidden in the syllabus but being tested a couple of times. And your understanding is also very important in these assumptions. Why? Because of the fact that sometimes you have to make a call in an examination sum, assuming the, moving with the given facts of the exam. The examiner will say there are no there are some errors are minimized, there are some residuals are assumed to be normally distributed, but you may think, okay, those are some just jargon he has given, but don't forget the fact that he or she is guiding you to the fact that you can use the ordinary least squares method to do this calculation, or this regression has been done by using this method. We'll go through one by one carefully and understand what they are going to tell you and the rationale behind it. Excuse me. Yeah, the first one. Dependent variable y can be calculated as a linear function of one or more set of independent variables plus an error term. This is the very fundamental assumption as to how we have laid this equation of y equals alpha plus beta x. Alpha plus beta x plus epsilon. This is the very fundamental assumption. Okay. What does this tell you? It is a linear function. If it is a curvilinear function, no, this is not the form. For me to show you a curvilinear function, sorry, previously software got little stuck. This is a good example. It's going to be y equals ax square plus bx plus c. This is the x-axis and this is the y-axis. If you could recall your early days of mathematics, we all have drawn this kind of graphs. This is a curvilinear. At a particular value, you can find a maximum value, peak. Another form, negative. Another form, exponential. Now this is the one, y equals e to the power x. Y equals e to the power x. Similarly, there can be many more different types of relationships which are not linear or non-linear relationships. There are, of course. Even the logarithmics, if you take certain relationships of variables, can be found that there is a logarithmic relationship. You take the x value, you take the log x value, and that's the birthplace of the y. You take the x value, you take the ex value or the exponential value that I just drawn here, that gives you the relationship. For instance, one good example that I can quote is for those who have learned this some of this production theory. For a worker that is working in a particular line, let's say a factory line, let's say he or she is a sewing machine worker. The particular task is to sew a particular piece of cloth or a button or any accessory to make sure that the piece of cloth is complete. If you look into the time that is being spent by that person to sew one piece of that garment, and if you measure that time from one garment to the second garment to the third one and so on and so forth, if you do that, what will happen is that, typically you can think, okay, there is going to be something like a linear negative relationship. Why? He or she is learning the job, of course, okay. And each and every one, once they are done with the sewing, he or she will quickly move to the next one. That assumption is pretty much rational. Okay, that's fine. But in reality, when you really study the theory, there's something called the learning curve. The learning curve is going to suggest you that that particular relationship is not going to be a linear negative relationship, but a exponential kind of a relationship. In nature, if you draw that, the form is going to be something like this. At a certain level, it is not going to be go further below this. I mean, if it is a negative relationship, it has to be something like this. This is not the one, but this is the one. Okay. Just want to quote the fact that uh, okay, the very first assumption is nothing but the linearity of the relationship. We are assuming it is linear. There is no any other relationship. But in reality, if you take the temperature of a particular town and the electricity usage, I mean, we can assume and move on with a linear relationship and take a prediction. But in reality, it may have had a different form of relationship. So how does a mathematician can find it? Of course, there is no any other way, trial and error, and use many mathematical, methods to find a perfect relationship. There is no particular one method. Second point, there are no definite linear relationship between independent variables. Now, this point, it is not for the simple linear, but for the multiple linear points. We will be learning the multiple one, but for the moment, bear with me and try to grasp this point. X1, X2, X3. Now, these are again going to be some independent variables. What does this point is going to tell you? We have to discuss this thoroughly and understand. What does this point is going to tell you? This is going to tell you that there is no definite linear relationship between the independent or the x variables per se. Now, you are, I mean, I can understand you haven't seen the multiple formation yet, yet to see it, but for the moment, assume that if at all there are some linear relationship between two independent variables, what is going to happen? I mean, the two variables that we are going to discuss, this x2 and x3, are going to move alone in a nice pattern. That means, students, those two can be combined and collated to one new variable. I mean, there's no x2 and x3 altogether, but rather it is going to be maybe x4 or x5 kind of a one. Okay. So this point is very important to understand that there are no linear relationship between the independent variable. The third one, no correlation between independent variable and the residuals. What does this going to tell you? If at all you know how to run a correlation now, you know how to calculate the correlation. If you take the residual value, this epsilon value, and if you take the value of this independent variable, this x values, for individual x value there is a residual value, for the next x value there is another residual value. How do we calculate it? In reality points are all over the place and we draw a best fitting line. So for that x1, if you take that x1 to the line like this movement, we know there is a residual value, okay, for that particular x y, as in for that x2 y2 versus this residual value. But if at all there is any correlation between these two values, what does this going to tell you? That we are not at the optimum level. This exercise is not right, and yet again there has to be some more uh, relationship between the residuals and the independent variables. That means this correlation or this exercise, whatever this exercise that we have done so far, is not a complete one, because still there are patterns. The fourth one, sorry, let me present it again. Okay, for the moment, let me just share my PPT since this is crashing a couple of times. Okay, the fourth one. Residuals are assumed to be distributed normally. What does this? What are this going to tell you? Residuals are assumed to be uh, distributed normally. What do you mean by a normal distribution, students? Now we know when we plot the some sort of single variable to that of the frequency, it comes as a nice normal curve. We learned so far that sometimes it could be skewed, sometimes it could be courtesies, factors could be discussed, it could be moved here and there. There could be different natures. But what are these residuals that we are discussing? This is nothing but that epsilon or that error term. Now, here under this fourth point, what is that going to tell you? If you take that residual values out, if you just take those residual values out, what will you be left with? You will be left with numbers 2.7, 3.2, 0, or for a particular one, negative something. If you just take all these numbers and plot them in a scatter diagram, you take only these residuals or these error terms and plot it in a normal distribution. What is going to happen? You are going to find the fact that those values are also going to form a nice normal distribution. A nice normal distribution. What does this going to tell you? This is going to tell you the fact that okay, there is absolutely no any other relationship between these residual values. What is that going to tell you? Okay, our model seems to be a good model where uh, you know there is absolutely no any other relationship between the data points, but rather we seems to have found the optimum model. That is what the fourth point is going to tell you. Residuals are assumed to be normally distributed. Means of residual equal to 0 and variance is a constant value. The residuals I told you it could be negatives, it could be positives, and when you calculate a mean, when you add the negative numbers and positive numbers, everything, and divide by the number of items, theoretically it has to come to 0 or close to 0, provided that your method is a good one. And the last one, there is no correlation between residual values. It is similar to the argument in this normal distribution one. This fourth one is going to tell you fact that the residuals are going to be nicely put it in a normal distribution. And the last one is going to tell you that there's no correlation of these residual values if you try to find one. So the glimpse or the essence of all these six different assumptions, if I take you through, is the fact that we are going to assume that it is going to be a linear one and no definite relationship between any independent variables, no relationship between the variables and the residuals. Things are normally distributed and no correlation, and this mean is going to be 0 for the residuals. What is effectively being crafted here? It's nothing but the fact that there are no any other relationship between these x's and y's other than the one that we have plotted. Other than the one that we have plotted. That means it is the best fit under the ordinary least squares method. If at all any of these are going to be violated, that means the output of the ordinary least squares method is not a good one. Rather, there is another optimum one which you have to find. Okay, that's about the assumptions. And finally, we need to understand the interpretation part of this ordinary least squares method. Once you are done with the regression and once you find the alpha and beta, we are going to represent our finding in this particular way. Sorry, in this particular way, as y hat is equal to alpha plus beta xi. Because of the fact that xi values are going to be uh, sort of like extrapolated or sort of like moved to these individual yi points. So for these xi points, there is an actual yi point, but rather we are going to extrapolate those values to yi values. I mean this line is not actual xi and yi. It's not this actual xi y values, but rather we are going to move this to this yi bar value. Okay. Because of the fact that we are going to represent, we are going to forget the fact that it is scattered, and we are going to represent these individual points with this equation that we found. And these definitions of alpha and beta is nothing but the same of a normal line. Alpha is the intersection, beta is the gradient. That means now we have come to this point of defining, okay, beta is the, sorry, this height is the alpha, and this angle is going to be the beta. Simple line. We are done. Ordinary least squares method, this is the output, and this is how we are going to express. We will spend some time, we'll spend some time on one of these one of these examples, and discuss for this given particular scatter points how we can use the least squares method and find the best fitting line. But don't worry, I've never seen in a very recent past examination paper, maybe like 3 to 4 years ago, this being tested, but rather don't forget the fact that examiners can be always be creative and ask for a new set of style of questions. Okay, so because of the fact that it can be tested, I wanted we all to take this example and calculated the best fitting line using the our beta and alpha and the covariance variance and the finding of alpha with by hand method. Okay, fine. I'll take a different plane and write these numbers, and we will try to do a regression and find some answers here. Okay. I have the values of x's and y's. I'm going to write it with you. X variables and y variables. X is 1, 2, 3, 4, and 5. And the corresponding y values are 2, 4, 5. This is 4 and 5. If I take a moment and try to do a real plotting, just for your understanding, this is the form that is going to be. Okay, this is x. If that is the case, I'm going to plot 1, 2, 3, 4, and 5. So for the y variables, the maximum value is 5. Let me just plot these numbers: 1, 2, 3, 4, and 5. Okay, students, we have a plane, and now I'm going to plot the numbers in the scatter graph. This is the real scale. Yeah? 1, 2 is going to be one particular point, so it's going to be here. 2, 4 is going to be another point. It's going to be here. 3, 5 is another point somewhere over here. 4, 4, another point over here. Last one, 5, 5. See, actual points, actual scaling, and this is the data set. Can you find a best fitting line here? I mean, a nice linear line. Can you do it like this? No, you can't. There may be another optimum one. If you do like that, maybe this particular line is going to be a better one. Maybe this is a better one. We really don't know. I mean, we can't really eyeball it and take a decision here also. That's why we are going to use this particular method and find this optimum best fitting line, which will be something like this. We'll see. Okay. What do we know so far? Is we know the fact that this line is going to be come in a form of y equals alpha plus beta x, plus there may be epsilon, there may be error term, but once we are done with the formation, we can omit the error term. Why? Because of the fact that we are minimizing the error term. So we know that beta and alpha can be calculated. How do we calculate beta? If I write the equation for your purview, beta is going to be the covariance divided between x and y divided by the variance of x. Rather, formation is going to be sigma xi minus x bar individual values multiplied by yi minus y bar value divided by sigma xi minus x bar. I'm taking the square. So what do we really need to find is the xi values, and yi values are the values that I have here. So what do we need here? We need these bars, isn't that so? We need these bars to be calculated first. How do you do that? Simple. We add all these numbers up and divide by 5. Why? Because there are 5 data points. So x bar is going to be 3. 1, 2, 3, 4, 5 and divide by 5. So similarly, y bar here is going to be 4. Take out your calculators and calculate with me. Huh? Okay, so I know the xi values, I know because of the fact that it's given data points, and x bar and y bar values, okay, fine, I just calculate. Now, what do I have to do? Simply follow the steps and find the ingredients or the components for this particular equation. Simple as that. So we'll take one by one and try to compute these points. So first one I'm going to select is going to be xi minus x bar. How do I calculate it? I have the xi column here and I know the x bar value over here. Xi column individual 1 minus 3 is going to give me a negative 2. 2 minus 3 is going to give me a negative 1. 3 minus 3 is going to be 0. 4 minus 3 is going to be 1 and 5 minus 2 is going to be 2. Fine. One aspect is completed. So the second one is yi minus y bar. Similarly, I know the yi values, it's over here, and I know the y bar value, that is 4. So individual values, I'm going to take the negation. So 2 minus 4 is going to be negative 2. This is going to be 0. This is going to be positive 1. This is going to be again 0. And the last one is going to be 1. Sorry. Okay. Those values are also computed. So I think I have the individual components of the variance equation. All what I have to do is I have to take the multiplication of these two columns that I drew so far and calculated this xi minus x bar to the yi minus y bar. So that means, students, for these individual points, I have to calculate the give me a moment. Yeah, sorry. So for these individual points, I have to calculate the multiplication. Negative 2 into negative 4 is going to be positive 4. Negative 1 into 0 is going to be 0. Wherever zeros are there, the multiplication is going to be 0. 2 into 1 is going to be 2. This is how I calculate the multiplication. So logically, this part is done and complete. So all what I'm left with is that calculate this xi minus x bar, and I have to take the square to calculate the bottom part of the equation. So far I have this highlighted area computed, that is xi minus x bar. So all what I have to do left with is calculate the xi minus x bars to the square. That means merely I'm taking the square root value of this point. I'm taking negative 2 to the square as positive 4. Similarly, negative 1, 0 is 0, 1 is 1, and this is 4. Now I have the individual values for the top part of the equation and the bottom part of the equation. This is the sigma is going to be 6, 4 plus 2, and the sigma over here is going to be 10. 4 plus 4 plus 1 plus 1. That's all the ingredients I need to calculate the beta. If I apply this knowledge to the equation, I have the top part as 6 and the bottom part as 10. So students, this is going to be 0 0.6. The beta is 0 0.6. Okay, are we happy now? No, not yet, because of the fact that this equation has two parts, y equals alpha plus beta x. Now the beta we have calculated so far. Now we know we can calculate the alpha simply by replacing the beta and applying the average points. I know the y bar, I know the x bar. What are the values? The values are y bar is 4 and x bar is 3. Y bar is 4, alpha is here, and beta is 0.6. I just calculated, and x is going to be 3. Now for that particular data point, I can calculate alpha as 4 minus 1.8. This is going to be 2.2. Beta is going to be 2.2. Now are we happy? Of course we are happy. Now with the error term, we don't know the error yet. We can define this equation is going to be y equals now alpha is 2.2 plus beta is 0.6 to the x. Y hat, if I just use the wording y hat, I don't have to write the epsilon or the error term. If I just use y, I have to add the error term also. This is the equation I just compiled. This is the output of the regression. That means for all these individual data points, so for all these individual data points of this 1, 2, 2, 4, 3, 5, 4, 4 and 5, 5, this scatter diagram that we drew here will be represented or will be replicated by this equation of y hat is equal to 2.2 plus 0.6 x. That's about it. That's a simple classic example of how to calculate the best fitting lines, best fitting lines, individual components of alpha and beta using the ordinary least squares method. Okay. Continuing with our discussion, so far we have calculated the simple linear regression. But students, don't forget the fact that the other aspect of our discussion is that multiple linear regression. So here it is going to give you an instance of for a given particular variable, it will be having more than one individual variables, more than one independent variables that is going to determine the value of the dependent variable. Okay. Sorry about the small typo. This is going to be bk and xki. Okay, sorry. When I done the subscript and superscript, messed up here. Yeah. This is the model that we can find for such a relationship. Now, previously, if you look at our previous discussion, what did we come up with? We came up with this y equals alpha plus beta x plus the error term. So here, this beta x has been multiplied. Sorry, the multiple times of beta x can be seen here. This is one instance. This is another instance. This is the kth instance. And the rest of the items, if you carefully look at it, is still there. Beta is there. So if this B0 is this alpha. This epsilon is this epsilon. And y is y. If I take you through the points, it says multiple linear regression or MLR is a statistical technique that uses several independent variables to predict the outcome of a dependent variable. Multiple regression is an extension of ordinary sparse regression, which uses only one explanatory variable. Let me, forgetting about these complex equations, let me just give you a real world example. I'm quoting this from one of the recent exam papers. This is the nature of a multiple linear regression output going to be. Let me take this from the paper. The profit. This is my Y wave. Profit is going to be 75,000 minus 1.2 times delivery cost plus 26,000 number of newspapers minus 15,000 number of pages per paper plus or minus many more other items. What are these? Delivery costs, number of newspapers, number of pages per newspapers. What are these two things? These are the individual X components that we discussed. So these are nothing but those X1, X1, X2, and X3 that you saw. X3. This is the Y. Now, what does this going to tell you? I mean, forget about the multiple linear regression. What this is going to tell you? If the delivery cost, if the delivery cost is going to, I mean, we don't know the number. Okay, delivery cost is a variable. For this particular month or for this week or for this day, the delivery cost may be a particular number. Okay, let's say the delivery cost is 10,000. That is going to give you an indication. Okay, the profit, whatever the profit value, will be declined by 1.2 times 10,000. That means 12,000 rupees will be diminished by the profits. Okay. Number of newspapers, item number 2. Okay, we are going to talk about something like a instance like a lake house business where they are publishing in a kind of different number of newspapers. If they have more number of newspapers, if they are publishing Dinamina, Lankadipa, Divina, Sunday Times, and many more, their profit is going to be increased by 26,000 times of the number of papers on that day. Say for a day that they're not publishing one particular paper, their profit is going to come down by 26,000 multiplied by the number of newspapers that they're dropping. Similarly, if the number of pages per newspaper is high, X3, that is going to give you the negative profits. But can you have, zero delivery cost, zero papers, and zero everything? You take out all these components out, and we only say, okay, if we don't do anything, we'll be left with 75,000 profit. No, that's a very absurd argument. That is not a viable instance. But provided all the other variables will have some values, the profit will be determined by this particular equation. So it is the same form of output that you have seen here in this complex model with these hats and i's and all these numbers. The regression equation is going to be nothing but, I mean, instead of this general form, now omitting this error term here, once we find the best fitting line for this particular this thing, I'm not going to call it as a linear line, but some sort of a line with a relationship. This now instead of this b, we can, I mean, it's your choice. You can use the b's or betas. It doesn't really matter. That's why I just use b here, just to show you that it's a general form. These constances, these b's I've shown here, will have some computed numbers. Now that 1.2, that 75,000, that 26,000, those are those computed numbers. And these x's will be just, they are lying out with the variables to come in. And with those variables, the outcome or the dependent variables value will be calculated. Okay. That's all about the multiple linear regression, and you really don't have to do a specific methodology to calculate, but rather it's very important. And if you look at the examination jargon also, this is the most examinable point in this lesson of multiple linear regression. The next week, when you do the sums, you will understand. Examiner will give ample number of different scenarios and ask, okay, are there any rationality of these numbers? What can you comment? That's one instance. I mean, if I take you to my this particular example I quoted from a exam paper, can I say, I mean, instead of this line of negative 26,000, this one, the red color highlighted. If I put a negative sign here, what does this going to tell you? It's going to tell you that if the number of newspapers are printing higher and higher, my profit is going to be lower. It's an absurd argument, isn't that so? If I have more newspapers, more profits, more readers, that means this is going to be a positive number. So this number cannot be negative. So those are the aspects that has been tested so far in the recent examination papers. That means examiner wants you to not to bang your head on the wall and calculate these lines, but rather he or she will give you the line, and then you have to express the accuracy, you have to express the coverage, so on and so on. We can move on quickly. Now we know the beta 0 or the B0 hat is the estimated interception. That's the value that theoretically all other independent variables are coming into 0. That's the value for the 0th point. And all these B1 hat to B1k are the estimated gradients for each independent variable. That is, when other independent variables are constant, the variation of that particular. I mean, if I take this newspaper example again for you to explain things, provided, now that's how we explain, provided all other, I mean, delivery costs, delivery cost, number of newspapers, and all these things are not moving, and we are only varying this particular 26,000. Now that's how we define this B value. That's how we define this B value in that instance only. We can't move these delivery cost and all these items together and define a B value, but rather all these B values are going to tell you, provided all other independent variables are constant, variation of that particular B value is going to be the number of times that the Y variable is going to move. Okay, that's the explanation for the intercept and the individual gradients. Okay, moving on to the last couple of parts on our discussion. Now we are going to discuss about this coefficient of determination. Similar to our correlation discussion, this R square is a value that can be calculated for each and individual lines that we are going to bring in. It could be, a simple linear, it could be multiple linear, but for any of these values, there is a R square. If I take you through to one of our previous graphs that I've plotted here, right, look at this one also. I told you here for the moment, let's forget about this R square, but here we are going to learn about this R square. If you look at carefully, let me highlight. I'm sorry, put up asterisk. See here, there's an R square value of 0.641. So for any line, it could be a simple linear regression, it could be multiple linear regression students. Now we can define this R square value, which is going to tell you for the reader how good is our model. I repeat, how good is our model. Rather, we can call it as a goodness of fit. Goodness of fit. We'll learn how to calculate this value in a while, but for the moment, let's try to see what this is going to tell you. R square is a measure which explains how much variability of one factor, can be caused by its relationship to another factor. Can be caused by its relationship to another factor. Means if I take just y and x. Now, theoretically, this r square is going to tell you if this for that particular graph r square of 0.68 or something. That means this is going to give you an indication. Okay, approximately 68% of the moments of x is being reflected with the y. Approximately 68%. So there is a 32% missing. So those cannot be visible or cannot be seen in y. Can that be? Of course. Of course. Provided, unless otherwise, it's a perfectly best fitting line and all these individual points are lying here. Except for that case. And the moment you see all these lines, sorry, these green dots I'm putting here, the moment you see all these points are here and there. So there's a 32% chance that some of these x variables movement cannot be, determined by the movements of y variable. Okay. That's the idea of the R square. How much or what sort of a percentage of movements of the independent variable and the dependent variable can be seen in the model that we just found out. Okay. So the higher the R square number, last point, the higher the R square number, it's a good one. There are plenty of questions at the examination giving you an R square value by the examiner and asking an R square of 86%. Do you think it's a good one? So you can comment, of course, close to 100, it's a good one. And the examiner can again ask, okay, now this guy, the researcher, has done some further research and found another best fitting line. And now the new R square value is going to be something like 0.92% or 0.9292%. Previously it was 86%. Now this is better. 92% is much better compared to the 86%. Why? Because of the fact that 92% of the that independent variables can be explained by the movements of the dependent variable. And the range of this R square is going to be between 0 to 1. It's going to be between 0 to 1. So what do you mean by the 0? It's an absolutely bad line. There's no absolute relationship. So none of the movements in x can be explained by the y. If it is 1, it's a perfectly fitting line. So all the data points are going through. If it's a simple linear regression, nice line. If it's a multiple linear regression, different panes, different lines. If it's a curvy linear, that can be also an instance, but it's perfectly explained. Okay. So most of the time, look at this example of R square of 0.86. Now this is the typical nature of what you can find. But even look at this actual data set of that GDP forecast. The R square is still 68%, not a perfect one. But it is strong enough to want to argue that it is more than 50% and you can find some sort of a correlation. We call this R square as a coefficient of determination. Okay. Now this is the way that you can calculate the R square. R square, or the coefficient of determination for two variables, can be calculated by this y hat minus y bar, the average, to the y minus y bar. On the top side, this is y hat. On the bottom side, this is y. Where are these y's and y hats are coming from? Is simply this y hat are the estimated values. These y are the actual values of the data points, similar to our previous point of this y's and y bars. Okay, so yeah, towards the end of it, we will take a moment and try to calculate this r square for a two variable example. I mean, r square can be calculated for multiple uh, regression also, but don't forget the fact that for that multiple regression also, when we are going to explain one particular variable, we have to isolate that, assume that all other variables are not going to change, and then discuss about that particular given variable like in a nice xy plane. Similar students, assume now this is the same previous data set 1, 2, 3, 4, 5, and this 2, 4, 5, 4, 5. If we use the same particular data set and try to calculate the R square, we will try to do it and wind up the class afterwards. Okay. The equation that we found previously for this data set is going to be y equals 2.2 plus 0.6x. We know that. We know this, and we are going to calculate the R square for this particular data set and see how much of a data set are being covered by this particular line. Okay. Similarly, let me open up an empty plane and do the numbers. Now we know it's a simple computation, but for the completion's sake, I just want to take you through the numbers. We know R square is going to be y hat minus y bar. We take the square, and the bottom part, we take the individual y values and take the square. This is the equation we are using. Okay. So I know the individual values of xi's and yi's, and I'll start from there. Xi 1, 2, 3, 4, and 5. Yi's are 2, 4, 5, 4, and 5. Okay. Similarly, we will move on with the computation. I think this is an easy one. We can, okay. We know the, we just need the y bar here only. We know the y bar is 4. Add all these numbers, divide by 5. That's how we calculate y bar. So we can calculate the individual points. So first we can calculate the y minus y bar. We know the individual y values, and then we know the y bar as 4. Okay. So simply we're taking the 2 minus 4, that is negative 2, 4 minus 4, 0, 5 minus 4 is going to be 1, this is 0, and this is going to be 1. The next step would be to take the square value of it. That means y minus y bar, we take the square value. 4, 0, 1, 0, 1. I'm going to need the sigma of this, and I'm keeping this aside. And then now this is the important point. We need to calculate this y hat for this next part. How do we do that? We don't know the y hat so far, but all what we know is yi. But we know by using this particular data set, in our previous working example, we calculated the equation for this as y equals 2. Y hat is equals 2.2 plus 0.6 times xi. If I write it precisely, xi. We calculated this. That means we can use the individual x values for these particular points, these x values, and apply it to this equation and calculate the y hats. One example would be for the x value of 1, this is going to, y hat is going to be 2.8. How come? Y hat is going to be 2.2 plus 0.6. Now here I have applied part. That means this is 2.2 plus 0.6. This is 2.8. Now similarly, students, I can use this equation, substitute the xi values with the values in our first column and get the y hat values. Straightforwardly applying the numbers. This is 2.8. This is going to be 3.4. This is going to be 4.0, 4.6, and 5.2. Do the math on your own and try to see whether you are getting the same numbers. And then all what I have to do is to calculate the y hat minus y bar, and then take the y hat minus y bar, the square value. Okay. I know the y hat minus y bar is going to be these individual numbers minus 4. Negative 1.2, negative 0.6. This is going to be 4 minus 4, 0. It's going to be positive 0.6, and this is going to be 1.2. Next step is nothing but take the square value of all these numbers. Negative 1.2 is going to give me 1.44. This is going to give me 0.36, 0, 0. This one is also 0.36, and positive 1.2 is going to give me also 1.4. Lastly, I have to take the sigma of this. This is going to be 3.6. Done. These are the individual elements I was looking for to be applied to this R square equation. This and this. If I just apply these numbers to the R square equation, I will be left with 3.6 divided by 6.0, and the answer is going to be 60%. This is the computation. What is this going to tell you? If I sum it up all this discussion so far, for these individual points of 1, 2, 2, 4, 3, 5, 4, 4, and 5, 5. For these individual data point students, the regression line can be calculated like this. Y hat equal to 2.2 plus 0.6 xi. And the equivalent R square is 60%. That means with this equation also, I mean, can we find optimum equation than this? We can't, because we find this using the ordinary least squares method. This is the optimum one. I mean, from our knowledge level point of view. So even for this equation, students, we can only explain 60% of the movements of x by y. That's the summary of this R square. So R square, or rather, if I use the word, the coefficient of determination is going to teach you. The coefficient of determination is going to teach you the goodness of fit, or variability of one factor, how much can be caused by its relationship to the another factor. Or in simple terms, we can call this as the goodness of fit also. So higher the R square, we are happy. If it is lower or average, close to 50%, we are not really happy. That's about it. Long lesson, a lot of numerical computations, but if you really look at the summary, it's all about there is only two types of relationships that we are discussing here. That's a simple linear regression and multiple linear regression. Let me take back you to the summary page quickly. And we learned that, okay, for any given types of relationships, we can simply apply. I mean, there are multiple methods to use to find this linear relationship, but simply we can use this ordinary least squares method, one of the easiest, one of the simplest and the basic models, and calculate a best fitting line. And for multiple linear regressions also, different planes. It's not like xy, but like xy into one plane, xz into another plane. So it's sort of like three-dimensional, multi-dimensional discussions. We can't really plot these numbers and find a relationship, but rather there are different software, there are different methodology, like SPSS, and running some statistical methods to find the variables of the multiple linear regression. But for our knowledge purpose and for examination purpose, always remember you will be mostly given the multiple regression formation. You need to understand what it is. You need to understand the lines, the signs, the positives and the negatives, and the interpretation. And lastly, we can calculate this coefficient of determination. So for that particular value of maybe 90%, maybe 60%, you have to be ready with your explanation to say whether it is going to be a best fit, to what degree, and provided we find a new line, compare those two R squares and comment things like that. That's the essence of our lesson for today. So for the plan for the next week is that we will spend ample time, go through all the different styles of examination questions under this particular lesson and wind it off for the session. If there are any questions to be discussed, I will be happy to stay some more minutes and answer any queries. Yeah. Did you use mean value for both? One moment. Did you use mean value of both x and y to calculate alpha or any given two numbers in the example? Yeah. Here, Ashel, what I have done was that I have used the x bar and y bar. I mean, of course, I can use a different values of xi and yi and calculate alpha. But what will happen in such instance? I will be calculating alpha for that particular point. Eventually, what will happen is that if I, use a different point, maybe let's say the second point of x2 and y2, or maybe x5 and y5, the alpha value will vary in such instance. But what is x bar and y bar in our class example? That is going to be the fundamental value that we started to cultivate this line. Okay? These xi's and yi's, those are numbers which were varying without any pattern. But if at all, instead of this any other values, if we use individual values, what happens is that the equation or the line will be somewhat biased and is set up. So that is the only reason why we need to typically use the mean value of both x and both y. It's correct. Uh, Sorry, I couldn't forget I could clearly mention the fact that if you use any other factors of xi and yi, it is going to give you a different alpha. So we have to always use the x bar and y bar. You're welcome. There are some interesting videos which I also found out in YouTube by some advanced statisticians like in foreign universities, which I used to create some of these materials also with you. What I'll do is I'll try to share some of them with your Google Classroom chat. Hopefully you can go through and I mean the explanation students that I can limitly do with you is a two-dimensional one. So there they have used some nice animations and shown this how these ordinary least squares methods and all are being computed. So since we are lacking of the time in this 2 hour, I'm not at liberty to share those, but let me share some of these publicly available links with you so that you will have a better understanding on the OLS. Okay, if there are no any other questions to be discussed, I can wind up the class for the day and be ready. You have the slides, you know the exam questions. If you have time, I will be more than happy if you have attempted maybe one or two so that you will be at a better position compared to our other fellow students when we try the questions on the next week. Okay then, so shall we wind up the class for the day then? Okay, so stay safe and have a good evening. Bye-bye.